online estimation of optimal treatment allocation strategy for the control of white nose syndrome in bats.
Great. Thank you. Is the mic working? Can you hear me okay? Okay. Yeah, I tried to put the original title on the slide and it took the whole thing, so I thought this was at least better looking. So thank you all for staying. I know it's the last talk, or second to last talk. And it's related to the previous talk, which I thought was great. So before we start, I just want to thank all of you for being here, and thanks for the invitation. So thanks to the editors and the organizers. This is joint work with a lot of different groups. I won't go through all of them. I just want to point out that the people who did the real work are here. That's Tao Hu and Nick Meyer. Those are the students. So this is part of their thesis work. Okay, so what is white nose syndrome? This is a disease that affects bats in North America. Actually, it's here in Europe, but it doesn't seem to be nearly as fatal, which is kind of an interesting thing. So it's highly fatal in North America. And so I pulled some recent headlines. If maybe you haven't seen this, you can see they're not very sunny. So fungus that's killing millions of bats isn't going away. White nose syndrome has almost completely wiped out some bat colonies. We went to one in North Carolina, and we went to the bats, and there was like 20 bats. And I said, "Oh, how many used to be here?" And they said, "Oh, like 100." And I said, "Oh," and they said 100,000. Right? I mean, it was just devastating. I mean, it just kills them at enormous rates. It's 90% fatal for some species. And this is a picture of a bat that has white nose syndrome. It's hanging upside down. Its feet are here. Its muzzle's there. You can see some white on its muzzle. So they hibernate, and this fungus grows on them, and they don't clean themselves when they're hibernating, so it just sort of grows unchecked, and it destroys the membranes in their wings, and it dehydrates them, and they die. And so ecologists and biologists are interested in applying interventions that will help prevent the spread, and this is one of them. This is an artificial cave. So you put this cave there, the bats hibernate in that instead of a cave, and the nice thing about an artificial cave is you can spray it down to fungicide, which you can't do in a regular cave. And just an interesting bit of trivia, they make these out of Corvette byproducts. So these, they're very expensive. They're about $1 million a piece. Okay, so here's the problem we're interested in, and this is the problem that these ecologists came to us with. Here's a map of the U.S., and the outlined regions are counties that have caves that house hibernating bats or mine shafts or other structures. And it's showing the spread color-coded by time, so it starts off in red, which is up here. This is Schoharie County, New York. It goes to the northeast and then down and across the Midwest. And so the problem is as follows. Every year they go out and they measure information about these regions, includes things like what species are there, how many caves are there, winter temperature is important for the spread of the fungus, human traffic, other things. They tell you where the disease is, or at least where they think it is, and how long it's been there. And then you choose a subset of locations to apply a treatment. You go forward a year, you look at the map again, you remeasure everything, and then you get to either keep your treatments where they are or you can change them. Okay? Now the ideal thing, of course, is to treat everywhere all the time. That is very expensive and you can't do that, so you have to choose a subset. And so the goal is to construct what I'll call an allocation strategy. And this is a map from the current epidemic status, so everything you know at a given time, to a subset of counties marked as high priority for treatment. Mathematically, we're going to assume we actually get to choose the counties, whereas in reality, you just recommend them and they sort of do whatever it is they're going to do. Okay, so a lot of problems have this form. The spread of human disease is an obvious one. We work in cholera, we work in flu, Ebola, malaria. Wildlife management's another one, allocating catch sizes. Adaptive conservation, so we work in planning for conservation areas in Puerto Rico. Forest fires, so when and where to do control burns, so we have a project in Australia on that. These two we don't work on, but others are doing this. So crime prevention, so you put police officers where you think there's going to be crime. So in the US they call this cops on dots, so the dots are like where the crime is expected to happen, you put a cop there. And then precision agriculture, so you can adjust the nutrients over a very fine spatial scale. Okay, so the idea is it's not just plots of land anymore, they can lay it down to what they claim is like a square inch. Okay, so why are these problems hard? In particular, why is white nose difficult? Well, in terms of the data, at the start, this is an emerging infectious disease, so you don't know anything about intervention effectiveness at time 1. So you don't know how the disease is spreading. So you have to estimate disease dynamics. You get noisy, incomplete, sparse measurements. You don't really know where the disease is or when it got there, right? There's human error. They don't go out there all at the same time, so they go at their convenience. These are U.S. Fish and Wildlife agents and Department of Natural Resource agents. I'm going to ignore that completely and assume that we see everything. It's very high dimensional, so in white nose syndrome there's about 11,000 measurements per time point. In terms of statistical estimation and inference, this is an online problem, meaning we are estimating the model and we are taking actions at the same time. Okay? So there's always this trade-off between taking actions that give you good information gain, which is what I think the last talk covered very nicely, and then doing what you think is best given your best guess at what the dynamics are right now. Okay, so you have to trade those off. And then what this means is you have this continually changing data-dependent strategy, and so the sampling distributions are complicated. In terms of computation, so if you can treat or not treat every location, there's 2 to the L, if L is the number of locations, possible treatment. So if L is 1,000, like it is in white nose syndrome, there's more treatment possibilities than there are atoms in the universe, right? So you can't enumerate all the possible choices. And keep in mind, you're not trying to plan for right now, you're trying to plan for an infinite time horizon. Okay. So just a quick outline. I'm going to first talk about what do we mean by an optimal allocation strategy, so formalize that using potential outcomes. Then I'll do the simplest possible thing, which is how do you estimate the optimal strategy if you assume a parametric dynamics model. So you assume that everything is characterized by some low-dimensional parameter vector, and then you just have to optimize. Then I'll see if we can get away without a dynamics model, and then I'll do some illustrative experiments. Okay, so just to formalize things, we'll assume we have a finite number of locations, which I'll denote the set of them by script L, and we'll label them 1 up to capital L. And then this is a process we'll assume is evolving in discrete time, so 1, 2, 3, and so on. And then at every time t, at every location little l, you observe a state, which I call SLT, and that's an RP. You observe an outcome YLT, which is real valued. You have an allocation, so this is whether or not you treat location L at time t. We'll call it 0, 1. And then we'll omit a subscript to denote the collection over all the locations. So ST would be the set of all states at all locations L, but we take the entire collection of locations. So it's all the states at time t. And then AT would be a vector of length L of zeros and ones and so on. Okay. And we're going to assume the allocations are based on ST at time t. And I want to point out that this is not really so much an assumption about the nature of the generative model that is being Markov. It's more that we've correctly summarized the past and called it the current state. Okay? So the state at time t isn't just what you observe at time t. It's all the information you think is relevant from the past, all collected and then summarized in this vector we call ST. Okay. All right, so we need to have a random allocation strategy. What I mean is, condition on all the information you have, it still has to be stochastic. And the reason is you have to learn what might have happened had you done something else. Just like in a randomized trial, we have to randomize treatment in order to keep learning. So if we have a deterministic strategy, we won't be able to improve. Okay, so to formalize this, let script B sub L denote the set of all distributions over binary vectors of length L. Script S denote the domain of the state. Then an allocation strategy is a map that takes as input a current state and gives you a distribution over allocations. So under pi, a decision maker who is presented with state st equals little st would select allocation AT with probability pi AT semicolon st. Okay, so it's just a distribution over all the allocations. So if you think to a sort of classic adaptive clinical trial, at every point in time, you adjust your probability of assigning treatment 1 versus treatment 0 based on what you've seen so far, and that's what's happening here. Only the allocations are, binary vectors of like 1,000. Okay, so we're going to focus on estimation within a class, capital pi, and this is how we're going to enforce things like feasibility and cost constraints. So that's going to go into that class. So if we can only treat, say, 10% of the locations, that class is only going to contain allocation strategies that have support over 10% of the locations. You can also factor in things like parsimony, interpretability, scalability. A lot of these problems I mentioned have political components, and so you have to adjust for those too. You have to have certain kind of equitable distribution of money across the area and so on. And the class we're going to consider has this form. Pi AS is an integral of indicator ES equals A. So E is a deterministic map from state to actions. Okay, so it takes as input a state, it dumps out an allocation. Okay, so these are deterministic. And then this here is a distribution over all deterministic maps. Okay, the reason we do this is because it's much easier for somebody, a domain expert, to give you deterministic maps than it is for them to give you stochastic processes indexed by states. So they give you deterministic maps that take as input the current state and dump out an allocation, and then we just mix over those. Okay? And so the question is going to be, what mixing distribution should you put here? It's going to turn out that the optimal one, in some sense, is going to be the posterior probability that deterministic strategy is optimal given the data you have. It's going to turn out that will be the optimal mixing strategy. Okay, so to formalize this, we use potential outcomes. So we use an over bar notation to denote past history. So A bar T would be A1 through AT and so on. So the set of potential outcomes I'll call W star is Y star T, that's the set of outcomes at time T, indexed by A bar T, the state, and that's over all possible treatment or allocation sequences over all times. And then at a potential outcome under the strategy pi is this convoluted expression, but I'll explain what's going on here. So Y star T of pi is the sum over all allocations, Y star T of that particular sequence of allocations, and then this product is just some indicators that say that the random allocation you got from pi is actually consistent with the sequence A. So it's just this is just going to be an indicator that picks off the sequence that would have been assigned from a random draw of pi. That's all that's happening here. This is being formalized. Okay, so for our criteria, we're going to look at the discounted marginal mean outcome under pi. So V of pi is the expectation of the infinite sum of gamma to the t minus 1 times some utility measure of the outcomes at time t under pi. So gamma is between 0 and 1, and so it's being exponentially downweighted. And the idea is you care about the future, but you care more about the present. Okay, so you're downweighting the future exponentially. There are other formulations. You could take an average reward, you could take a finite time horizon, and the methodology would all go through. And then U is some measure that takes the entire vector of outcomes and summarizes them, like footprint of the disease, or cost of managing the disease, or number of infected bats, that kind of thing. And the optimal strategy maximizes this. So I guess it wouldn't be number of infected bats, number of uninfected bats. And so V of pi opt is the optimal regime is at least as big as V of pi for all pi in your class. So the optimal is defined as being within this class you're considering. Okay, so we need to connect this potential outcome definition with the actual generative model. So let ht be the history at time t, so that's all the states and actions and outcomes that have occurred prior to t. And the standard assumptions you would see in causal inference would be the allocation at time t is independent of the potential outcomes given the history, meaning that the decision made at time t is informed by the things you've observed. There's no unmeasured confounding. Consistency, so yt, the outcomes you observe, are the potential outcomes under the allocations actually taken, and the same with the states. Okay, so sometimes people don't like to have this called an assumption. It seems to be more true by definition. And then positivity. There exists an epsilon greater than 0 such the probability of selecting any allocation given the history is at least epsilon. And I said for all pi feasible AT, what that means is all the allocations you could choose based on the constraints that you have. Okay, so you don't need support on allocations you could never choose in practice. So the next thing that would happen, and this came up a couple times already, is you would assume something like SITFA, right? So there's no spillover effect. But as we heard in the last talk, we can't assume that here. There's going to be spillover effects. In fact, you hope there are spillover effects. You hope that if you are able to treat the disease in one location, you get some positive spillover. So we are not going to be able to assume that the entire collection of locations are independent and leveraged that way. So typical approach here would be to pool over locations. If we were going to try to apply existing methodology, we treat the locations as being independent. We do some kind of dynamic treat regime kind of methodology. But that doesn't apply here. So what does that mean? Well, if we take those standard causal assumptions without SITFA, we can still write down what the expected utility is at time t under pi, and it has this form here. The form is not important other than to note that we have different conditional densities at every time point, and we only have one observation per time point. So this is not non-parametrically identifiable, right? So if you have one observation per time point, you can't estimate two conditional densities, right? So, and even if we assume that these densities are the same over time, so the densities are time homogeneous, so you have the same density at every time, you still can't do this non-parametrically, at least from any practical point of view, because you'd be conditioning on a categorical variable that has 2 to the L values, and L is 1,000. So you would need so much data to estimate this that it wouldn't be possible. So, and this is probably clear from the start, you're going to have to be able to pool over locations somehow, right? So either implicitly or explicitly, you're going to have to model that spillover and incorporate it. Okay, so the simplest thing you could do in this setting would be to assume some kind of Markovian low-dimensional parametric model. So I'm going to assume that the density for the outcome, so this is the density for the outcome at time v, doesn't depend on v. And given the history, it only depends on the history through the current state. So you've done a good job of summarizing your state, and so everything else is irrelevant that happens before. And it's indexed by some parameter vector beta. And then, because of this, you'll need to model the evolution of the state. So the conditional distribution of the state at time v given the entire history doesn't depend on v, and it only depends on the pass through the previous state and allocation, and it's indexed by some low-dimensional parameter vector theta. Okay? So now we've reduced the problem to estimating beta, theta, and then optimizing. Okay, so here's the procedure. First, you construct estimators beta hat and theta hat of beta. Okay, so I'm going to assume we do maximum likelihood here. Then you draw beta tilde, theta tilde from the sampling distribution of beta hat and theta hat. I'll say why we do this in a minute. Then you simulate under these draws. So you can simulate the whole process, the disease spreading and the effect of all the allocations, to get an estimator of the outcome for any regime you put here, for any allocation strategy you put here. And then you use stochastic programming to compute E hat is the maximizer of this estimated outcome. And remember, this is a set of deterministic strategies. So it's easiest to see in a picture. Here's the picture. You start off, you observe state, you do maximum likelihood, then you sample from the sampling distribution of the maximum likelihood estimators. Simulation optimization, you get an estimated deterministic strategy. You follow that, you observe the next state, and this goes round and round. So you might recognize this as Thompson sampling. This is a very old idea. So what we're doing, the reason we're sampling from the sampling distribution is we're treating this as a surrogate for the posterior. So what you would do in full Thompson sampling is you compute the posterior probability that each deterministic strategy, E, is optimal. But that's very expensive. So what you do instead is you treat the sampling distribution of the maximum likelihood estimator as a surrogate for its posterior. You draw from there and you optimize. Okay? So this is like an approximate Thompson sampling algorithm. Okay, so that's the idea. Okay, so what can we say? So this is kind of a convoluted, computationally intensive process, so is there anything we can say? It turns out you can prove some things about this. I'm going to gloss over the details of the assumptions just to note that we're going to assume the parametric model is correct. We're defining pi opt as being in the strategy space, so this is the optimum within this space, and then some additional assumptions about the parameter space and the likelihood and so on. Okay, so let pi hat denote the Thompson sampling estimator at time t. So this is the allocation strategy at time t under that diagram I showed. And then we'll assume that these technical conditions hold and those causal conditions hold. If eta t is any sequence that diverges to infinity with t and is little o of t, then you can show the difference between the outcome under Thompson sampling and the outcome under the optimal is big OP of square root of eta t over t plus gamma to the eta t. And in particular, you can choose eta t so that the order here is square root of log t over t. Okay, so those of you who have seen other kinds of sequential decision problems, like bandit algorithms, you'll know that that rate comes up, square root of log t over t. Okay? And it's unimprovable in certain circumstances. Okay, so one of the other things that people care about in this context is postulating a finite set of candidate dynamics models. So they have science telling them that the disease is spreading according to a finite set of models. So just have a handful of models, I think one of them is right. And if you're in that setting, so if capital pi is finite, for every pi in this finite set, define script b sub pi to be the set of parameters for which pi is optimal if those were the true parameters. So you partition the parameter space according to which policy is optimal. So if it's finite and those conditions hold, and the truth, beta star theta star, is an interior point of the set, then you can show the probability that the Thompson sampling estimator is not the optimal one. Remember, the optimal one is defined as being in this set, so it has to be in there. Decays exponentially. Okay, so it's less than or equal to k e to the minus c root t, and k and c are constants. And in fact, under additional conditions, you can replace this root t with a t. Okay, so you can prove that you do get the right thing infinitely often if you have a finite set, and you can also prove that you get the right thing asymptotically under weaker conditions. Okay, so just a few points. In terms of the pros and cons, it's intuitive, and I don't mean it's intuitive in that domain experts say, why don't you try Thompson sampling? I mean, it's intuitive in the sense that you can say, we're going to model the disease spread, we're going to put it in a computer, we're going to simulate what the best thing is to do, and that's what we're going to recommend doing. Right? So that sort of resonates with them. You're sort of simulating the entire spread of the disease. You can leverage existing theory, so you can use that to inform those parametric dynamics models. You get low variance, which is very important in these data-impoverished settings, at least at the onset of an emerging disease. You can extend this to non-stationary settings by having state space models. You can actually have sieves for those dynamics models and let those grow in complexity with data and so on. You can get asymptotic. You can show it's asymptotically optimal under what I would say are very strong conditions. But the devil's in the details, and so I'm sure, as Ben knows, this computation is non-trivial. So you're climbing uphill in this allocation space. So it's not necessarily a nice space. So you're climbing uphill in the space of deterministic functions. The induced policy, the class that you're actually optimizing over is a mixture over deterministic strategies. So even if the deterministic strategies are interpretable, the final mixture is not. Okay? So there are a number of potential drawbacks here. So that raises the question, can you get by without specifying a model for the way everything works, the outcomes and the spread of the disease and so on? So the idea is that parametric models are suited for large impoverished settings, but the data are accumulating, and as they accumulate, we can weaken dependence on a model. And we also don't need complete dynamics to determine pi-op. So pi-op is a function of a lower dimensional summary of the actual distribution. So the idea is you apply Thompson sampling for a while until the model, until you get enough data, then you switch to some kind of semi-parametric estimator that doesn't actually fully rely on the model. So that's the idea. So here's the idea. So for any pi, you can define something called the Q function. The Q function is, it's a function of state and action, and it's indexed by pi. It's the outcome you'd expect to get on average following pi if you were in state S at time t, and you chose allocation A at time t, and then you followed pi thereafter. Okay. So it's the goodness of choosing allocation A given you're in state S if you plan to follow pi infinitely after that. Okay. Define v sub r of pi to be the integral of this Q function if you choose your allocation according to pi against some, and there should be a pi here, apologies, against some baseline distribution r, called the reference distribution. Then you can show if r is a distribution in the initial state, vr pi and v pi match up. They're the same. So the idea is you estimate this Q function, which you can do, we'll see that we'll be able to turn this into an estimating equation that doesn't require the dynamics model, and then we can estimate the optimal strategy. Okay, so in particular, you can show for any function z that depends only on state and action, the utility at time t plus the discount factor times q pi, evaluated at the next state and pi, minus the q function at the current state and action, times the z is equal to 0. Okay, so this is always true. Okay, so this is an identity from the Bellman equation. And so we can turn this into an estimating equation. It's important to note that this expectation is over the distribution of the observed data. So we can replace it with an empirical expectation. It's not over a counterfactual distribution induced by some policy. So we postulate a model for Q, say QS A, and I'll say lambda pi. You set Z to be the gradient of this with respect to the parameters. Then you average over the observed data and randomness in your policy pi, and that gives your estimating equation. So in particular, if I define capital lambda t of little lambda pi to be this thing, this is an average over the data. This is an expectation in the stochasticity in your policy given the data. Then setting lambda of pi equal to 0 is an estimating equation which you can solve to get an estimator of lambda pi. And you can also add a penalty to impose additional structure. So lambda has the argument of lambda transpose lambda, and you can put a matrix in the middle here that may be, say, the expectation of Q transpose plus the penalty, and this is a tuning parameter. And then your semi-parametric estimator, say pi tilde, is the argmax of the integral of your estimated Q function. So you've plugged in your estimated parameters here, you integrate against a reference distribution, and now you've got a semi-parametric estimator. So you were able to construct an estimator that doesn't require the dynamics model. And so here's the picture. Observe S, build your estimating equation, that's this. Then you optimize to get pi tilde, you draw according to pi tilde, and this goes round and round. Okay, so that's the idea. Okay, so in terms of pros and cons, this has lower bias in the sense that it imposes less structure on the generative model. Fewer underlying assumptions. It's generally much faster than the previous approach because you don't have to do this giant simulation optimization. You can extend to non-stationary settings via state space models. You can also push all the theory through with standard estimating equations kind of techniques. You can use a penalty impose structure, but the drawbacks are complementary to the pros of the other approach. It's high variance, it requires more data. The incorporation of scientific theory is much more limited. You can't ask somebody what a Q function should look like in this setting, so you're not really leveraging that. And of course, it's more complicated. So a natural idea is to anchor the semi-parametric model to the parametric model because their pros and cons are complementary. So use the parametric model until you get enough data, then you switch to the semi-parametric model, and the goal is to trade off bias and variance. And as I mentioned, we call this anchoring the semi-parametric model. And so here's a very ad hoc way to do it. You have some function that just switches. So v sub t, or nu sub t, is going to follow the model-based estimator, and if this is 1, and the semi-parametric-based estimator if this is 0, and you just let this thing switch at some point. Okay, you could, of course, have something that's more smooth, a smooth transition. But we're going to do that where we just sort of switch over at a fixed time point for illustration. Okay, so some experiments. We'll simulate this. So we're going to finally see a network. So we have the word network has finally appeared in this talk. I don't even know how much time I have left, but maybe even over time before we get to network. Okay, so what we're going to do is we're going to infect 1% of the nodes. We'll let it spread for 6 time steps. And then we'll assume we can treat 6% of the nodes for a subsequent 8 time steps. We'll look at a generative model that mimics white nose, which is a variant of a gravity model, which appeared in Nature in 2012. And the coefficients are going to be, they're based on the white nose data, but we scaled them up so you get 70% of the network to be infected at the end if you don't treat anyone. And the states are going to be generated from a standard 10-variate normal, and they evolve according to an AR process. Okay, so for competing strategies, we'll look at doing nothing. We'll look at predicting where the disease is going to go next and then treating there. Proximal, this is the ad hoc strategy that was proposed by the U.S. Fish and Wildlife Service when they came to us. This is what they wanted to do. You find a boundary around the disease and you treat there. We'll look at simulation optimization, and then we'll look at anchored where you just switch it halfway. That's all. Okay, so we'll look at correct and incorrect dynamics model. So the correct will be a time-dependent SI model. Incorrect will be dynamics only depend on distance. And then we'll use what's called a probit rank class of strategies. Okay, here we go. Network pictures. There's the network. It's a grid. Maybe the least exciting network we've had the whole 2 days. We'll look at 100 nodes, 500 nodes, 1,000 nodes. This is how many are infected on average over 1,000 Monte Carlo replications. No treatment is 70 by design. Myopic is about 50% or 55%. Proximal is about the same, a little bit worse. Simulation optimization is considerably better on smaller networks and still considerably better, I would say, in the medium to large networks. The anchored policy is about the same. It's a little bit worse because it has more flexibility, and here the model is correct. Incorrectly specified model, no treatment's the same. Myopic is worse because it's based on an estimated model. Proximal doesn't depend on the model, so it's exactly the same. You can see simulation optimization takes a hit here because it's using an incorrectly specified model, where the semi-parametric estimator does about as well as it did with the incorrectly specified model. Okay, so here's another network, a scale-free network. And so now that we know sort of how to read the tables, I'll go a little more quickly. So this is no treatment. This is myopic. The proximal strategy did about as bad as myopic. Simulation optimization anchored did about the same and not much better than proximal. And then under the misspecified model, the simulation optimization wasn't hurt as much by the misspecification, but again, this was slightly more robust. Here's another one, nearest neighbors, 3 nearest neighbors. And here you can see that, again, these two performed the best. If you have the right model, simulation optimization is optimal. But if the model is misspecified, you do get some robustness from doing the semi-parametric model. So finally, to turn to the white nose data, this is, of course, what they were interested in. So we simulated the disease going forward from actually more updated data than this, 2015. So there's 1,137 nodes. Under no treatment, you get 60%. If the model is correct, simulation optimization is 30%, but if the model is incorrect, you go all the way up to 50. So actually, this is an example where the misspecification really seems to hurt you a lot. Okay? On the other hand, if you look at the anchored policy, it goes from 35, and this is Monte Carlo error, but it's about the same. Okay? So it looks slightly better, but obviously that's Monte Carlo error. The proximal strategy here is worse than myopic if the model is correct. So the U.S. Fish and Wildlife, sort of their initial thoughts on this is it's actually worse than just predicting where it's going to go and treating there. Although if you have the model incorrect, this is better. So it seems to give pretty substantial improvement, at least in this sort of simulated setting. Okay, so just to wrap up, I was really excited to come today because I think there's a lot of network information that can be used in these kinds of problems. And in particular, we're currently scaling it to very big problems, millions of nodes. And so there, this network structure becomes really important. You need to do divide and conquer, and you need to be able to divide the network in a meaningful way so that you don't incur too much loss in terms of the optimization. And there's a lot of different epidemics that can be posed as these kind of allocation problems. You need to account for spillover effect. It has to be implemented online. It has to be computationally feasible. There should be an asterisk here. I mean, this is not very fast, but this is on the time scale of a year. So it has to be feasible in the sense that you can do it. It doesn't have to run in milliseconds. It has to accommodate evolving logistical constraints. So when you're working with these kinds of agencies, the resources change all the time. And we looked at parametric and semi-parametric estimators. You can, of course, make these more flexible, but a non-parametric approach, a fully non-parametric approach is not possible because the model's not identifiable. So I think I'll stop there. Oh, nope, I had more to say. Oh, this is what I already said. I just hope I can get you guys excited to work on these problems because I think for someone who really has an understanding of how this network structure can be exploited, could really make a big impact. And there's just a ton of open problems. And so please do talk to me because we have lots of interesting things, I think. So thank you.
All right, so questions? Maybe I'll start with a question. The network, you haven't actually specified, well, you didn't say explicitly the network that you use, which obviously is a spatial network. Do you want to say how you construct that?
Yeah, so, and I think maybe I maybe pushed too hard that this was a network problem, because here it works in general if you have a distance, any kind of distance. So here, you know, it's fully connected as the network we had here. It's just that it's weighted by how far apart you are in space and ecological similarity. So actually that we have a distance in this example where it's not just physical distance in space, but also ecological similarity because the bats are moving to places that are similar. So we have an induced distance in this space. And even on these network examples, the disease is allowed to spread spatially, but the distance is organized geodesically. So that's how you sort of impose different spatial structure, but actually you can jump over lengths. So I didn't show examples where the disease can say only is spread along a link, but we do have examples like that too. Yeah.
Mm-hmm. Right. The questions? Further question? Okay. Ben?
You looked at sort of particle swarm optimization for allocating the or making allocations. That seems to be very popular in just about everything at the moment.
Yeah.
And it seems to fit in quite well with, you know, the fact that things flow down networks. It seems to feel the right kind of way. I haven't looked at it, but I just thought it might be computationally a lot easier than you know, deepest descent or whatever it is.
Yeah, so that's a good question, and we tried a lot of different things because the optimization problem is horrible. So it turns out that for some of these problems you can rewrite them as linear mixed integer programs, and so, but you have to sort of do term expansion, in which case the number of terms grows a lot with the size of the network. And so we did try that. That does okay for small networks, and you can guarantee that you have convergence within some gap. But it doesn't seem to be feasible once you get past, say, 500 or 1,000. We did try particle swarm optimization, and we found that worked okay. We had a difficult time tuning it, the swarm size and all this kind of thing. And then relaxation seemed to work well. So if you just, even though you can only treat or not treat each place, you just assume that you can partially treat places, and then you force those partial treatments towards the edges 0 and 1. So you treat it as a continuous optimization problem, solve it, and then keep resolving it and pushing the solutions closer to 0 and 1, which is sort of a classic mixed integer programming kind of technique. But yeah, it's a huge open disaster problem. We also tried the swapping, which didn't seem to work that well. But it seemed to do a little bit better in terms of solution improvement if you did something like stochastic descent and then did swapping. Yeah. Thanks.
Maybe one more final question that I have. So you mentioned the political constraints as part of your constraint in the sets that you had to So did certain treatments have to be spread geographically across the country or states or?
Yeah.
Yeah, can you say something about it?
Right. Yeah. The thing. Yeah. So that's the hard part. Is you don't know what's going to happen. You can sort of have a mathematical model, and then you find out that it's not feasible. So we also work in conservation planning in Puerto Rico, and so the other problem is you go and you survey the land and you figure out which parcels are used for what, and then you are trying to convert them. And so you might take a sun-grown coffee plantation, and then you give them some kind of government incentive to plant trees, either to make it a shade-grown plantation or partially shade-grown, or put some greenery that supports certain kinds of animals. But it turns out that if you and I are neighbors, and I give you an incentive, then I have to give me the same incentive, even though the effect of giving me the incentive might be much less than if I get you to do something. And so there's all these kind of constraints. And then if there's some district that's really a prime candidate for improving in terms of how it's going to change the ecological landscape, the person who sort of governs that district is very happy because they get a lot of money, but the neighboring district is very unhappy because they're not getting all these incentives. And so there's that kind of challenge that we really don't have any control of, but we suggest something and then we get pushed back and then we try to modify. And yeah, so so it's a hard challenge that we don't really know how to get past.
That's iterative optimization, clearly.
Yeah, it's another iterative layer on this whole thing. Yeah.
Okay, good. Any further questions? If not, let's thank Eric again.
Thank you.